focus on our lesson with ideal gas behavior. Okay, initially, in the initial chapter 5, we already talked about the different gases law, which is Boyle's law, Charles' law, Avogadro's law, which led to the derivation of ideal gas equation. Okay, so ideal gas equation is PV equals to nRT. Okay, so using this ideal gas equation, we believe under kinetic molecular theory of gas, there are two assumptions made for us to use this equation, which is the first one is all the gas molecules have negligible molecular volume, and secondly, there is no intermolecular forces that are present between the gas molecule. Okay, so we're going to look in details about this ideal gas behavior in this entire lesson video. Okay, so we're going to find out at the end of this video either there is really an ideal gas at all conditions, or some gases might behave differently under certain condition. Okay, so in reality, we have two types of gases. Ideal gas is based on what we learned in ideal gas equation, and in the reality, we name it. We also have this real gas. So what is the difference between these two? You're going to find out and understand about this both by the end of this chapter. Alright? Okay. So first, let's talk about ideal gas behavior. Is it real, or is it just a theory that we made or scientists made for us to understand that gas is an ideal gas one? Okay. So this is to emphasize to you what are the assumptions we made to understand ideal gas behavior, which is based on kinetic molecular theory of gas. So the first theory that we made for this assumption is volume of gas molecules does not occupy any space, which means volume of gas molecule is negligible. Okay, so that is the first assumption. Okay, so secondly, they do not attract each other. Okay, so do not attract each other means no intermolecular forces that present. Okay, no intermolecular forces that is present between the gas molecule. Okay, so if let's say you are still struggling to understand about intermolecular forces, don't forget to click on my video about hydrogen bond. So at that video, I explained to you about the various types of intermolecular forces that are present, and I elaborate in detail what is hydrogen bonding. Okay, right. So only these two assumptions that being applied based on the kinetic molecular theory of gas, and these two conditions must be met in order for a gas to behave ideally. Okay, so you always need to remember these two conditions. Okay, so we ignore the volume of the gas molecule, okay, and we assume there is no intermolecular forces present between the gas molecule. Okay, as we can see in the formula of ideal gas equation, PV equals to nRT. Okay, so this volume is referring to the volume of container. Okay, so it should be there is a volume of gas molecule, but to use up this equation, we completely ignore, okay, the presence of the volume of the gas molecule. Okay, we just need to consider about volume of container. Alright. So, at what condition does ideal gas behavior exist? Okay, that two conditions that might be met, you need to remember, which is the first one, volume of the gas molecule is negligible, and secondly, intermolecular forces between the gas molecules are negligible too. Okay, so for these two conditions need to be met, so the gas molecules need to be in a very high temperature as well as at a low pressure, because only when the gas molecules are far apart from each other, they cannot have any intermolecular forces between them. Okay. Secondly, the volume of the gas molecule become very small compared to the volume of the container, and we can ignore the presence of the volume of the gas molecule. Okay, so for a gas molecule to behave ideally, you need to remember the gas molecules okay, need to be very far apart from each other. Okay, only in that setup, okay, only in that gas molecules arrangement, we can have these two conditions being met, which is volume of the gas molecule become very small and we can ignore it, and secondly, there is no attraction or intermolecular forces present between the gas molecule. Okay, so it only can happen under two conditions: high temperature and low pressure. Okay, but in some cases, okay, what will happen when the gas molecules is not in high temperature and low pressure? Okay, so for example, when it is in the high pressure system, okay, as you can see in the first beaker, a low pressure, so all the gas molecules are separated from each other and they are being far away from each other. So this one far away. Okay, when they are far away, that means they can meet that two condition. Okay, so volume of the gas molecules become negligible and no intermolecular forces present between the gas molecule. However, when I push this piston, okay, when I push this piston downwards to the container, I'm going to compress or reduce the size or reduce the volume of this space. Okay, so volume of this space is being reduced. Okay, so when this space is being reduced, what will happen? Okay, so the system will have a very high pressure, and as you can see, the gas molecules become close to each other. Okay, what will happen when the gas molecule become close to each other? First, okay, so they can exert a intermolecular forces between the molecules. So there are intermolecular forces present between the molecules. They can attract each other. Okay, so attractive force is a kind of intermolecular force. Secondly, as you can see, the gas molecules become large in the space. It occupies certain space in the container, and we only have limited spaces between the gas molecule. That means now at this condition of high pressure, the volume of the gas molecule occupy a significant space in the container, and therefore we cannot ignore it anymore. Okay, so we need to consider gas molecule has a specific volume, and therefore we cannot neglect it from the ideal gas behavior. Okay, so when these two conditions happen, okay, at high pressure, volume of gas molecules becomes significant, intermolecular forces present between the gas molecules. Again, why? Because the molecules are very close to each other at the high pressure. Okay, so instead of becoming an ideal gas, it deviates from ideality. It deviates from ideal gas behavior. Deviates mean it moves away. It goes far away. Okay, so in a simpler words, we can say the gas no longer exists as an ideal gas, but now it becomes a real gas. So real gas behavior. Okay, for your information, okay, back to the previous slide. For your information, okay, gas molecules has its own volume. Okay, it depends on the size of the atoms that made up the molecule. Okay, secondly, the bond length in the molecule. So reality, gas molecules has its specific volume and we need to consider it. So that's why at high pressure, when the gas molecules volume becomes significant, okay, so it no longer behaves as an ideal gas, but now we call it as real gas. Okay, secondly, okay, gas will deviate from ideal behavior at a low temperature. Okay, why? Because at low temperature, okay, this is the hot air. Okay, gas molecules have high kinetic energy. Okay, so at hot air or high temperature, when the gas molecules have high kinetic energy, it can move freely far apart from each other. Okay, move freely far apart from each other. However, okay, so this one in the cold air, which is at low temperature, okay, at low temperature, the kinetic energy of the gas molecule is very low, okay, so kinetic energy of the gas molecule is low. So what will happen? Okay, so what will happen? Okay, think about it. If the kinetic energy of the molecule is low, what will happen to their movement? Will it move freely far apart from each other? Will it move in high speed? Definitely no. Okay, so the gas molecule will move very slowly because it doesn't have enough energy to move around. So since it moves slowly, it becomes close to each other. So when it comes close to each other, okay, what will happen then? They can attract each other. Attractive forces exist between them. And that attractive forces, we name it as intermolecular forces. So when this happens, intermolecular forces are present, automatically it already deviates from ideal gas behavior. So it no longer behave like an ideal gas, but instead it become a real gas. Okay, so as a recap, try to remember, okay, remember this. At high pressure and low temperature, the gas will not behave ideally. Okay, why? Because they become close to each other. When the gas molecules are close to each other, the gas volumes, okay, the gas molecules volume becomes significant and it occupies certain space in the container. Secondly, when they have become close to each other, the gas molecules can attract each other. Attraction means attractive forces, and these attractive forces implies intermolecular forces present between them. So it no longer behave like an ideal gas. Now we call it as a real gas. Okay, so these are the plot of PV over RT, which is from PV equals to nRT. Okay, so PV over RT equals to N. So N is our gradient. Okay, so as you can see, okay, this is a plot for nitrogen, methane, hydrogen, and carbon dioxide. Okay, so if let's say the N is 1, okay, you can see here this one is for ideal gas. However, these are the real graph or the real plot based on the experimental data that we obtain, okay, for nitrogen, methane, hydrogen, and carbon dioxide. Okay, so it only behaves as an ideal gas. Okay, look at this. Okay, at only a low pressure. Okay, only at low pressure. Okay, only at this around. Okay, at this stage and so on. Okay, at other condition. Okay, so this plot is considered at the constant temperature. Okay, so we only look at the pressure. Constant temperature. Pardon me with the typo, okay, at constant temperature. So we just need to see the various of pressure that we apply here, okay. As you can see, as we approach a higher pressure, okay, from left to right, all the gases goes far away from ideal gas, okay. If it's an ideal gas, it will just having a straight line at 1.0. PV over RT equals to 1, okay, which is the number of mole, 1 mole, okay. However, at a higher pressure, all the gases deviates, okay, goes far away from 1.0. That means which shows that increasing in pressure shows increasing deviation of the gas from ideal behavior. So at this high pressure, all the gas molecules are actually behaving like a real gas. Okay, let's look what happened when we vary the temperature, because we say that initially at low temperature and high pressure, all the gases will behave as. So this one is a different plot. If in the previous plot, okay, we see a plot of different gases at constant temperature, okay, but PV over RT versus pressure, okay, but this one, we're using the same kind of gas, okay, same type of gas, same molecule, gas molecules, but at different temperature, okay, so we have 200 Kelvin, okay, 500 Kelvin, and 1000 Kelvin, okay. We say that, okay, for a gas to behave ideally, okay, it needs to be far apart from each other, okay, far apart from each other so that the gas molecule volume can be ignored, okay, because it's too small. And secondly, there is no intermolecular forces present between the gas molecule, okay. Those are at high temperature, okay. Look at the 1000 Kelvin, okay. So it almost shows that it only deviates from ideal gas behavior at a higher pressure, okay. At a low pressure, you can see it still follows the ideal gas behavior, alright. But, okay, as we see, a decreasing in temperature, okay, so from 500 Kelvin, okay, to 200 Kelvin. So 200 Kelvin is the lowest temperature in this example, and it shows the largest deviation from ideal gas behavior. Even at a low pressure, okay, as this is an increasing pressure, it shows a sharp change in the value of PV over RT. It goes far away from 1. It goes far away from ideal gas. It deviates far away from ideal gas behavior. So in this plot, it shows low temperature and high pressure, showing that the gas does not behave ideally, okay, because the gas molecules become close enough to each other. So when they become close enough to each other, the gas molecule volume becomes significant, okay. If I draw a beaker, okay, so these are when the having at low temperature and high pressure. See? Okay, so the spaces between the gas molecules are too small, and somehow the gas molecules become very significant. So that's why we need to consider about the volume of gas molecule. Okay, and then since they are close enough to each other, they exert certain amount of attractive forces between them. So intermolecular forces present. Automatically, when these two conditions are present, the gas no longer behaves ideally and becoming a real gas. Okay, so you have to remember, only at high temperature, low pressure, the gas will behave ideally. But at low temperature and high pressure, the gas will deviate from ideal behavior and becoming a real gas. Okay, so when it becomes a real gas, PV equals to nRT is no longer a valid equation. Okay. No longer valid for real gas. Okay, why? Because this one, okay, to use PV equals nRT, we assume two things. Volume of gas molecule is negligible. Alright. And secondly, we assume no IMF between gas molecule. IMF means intermolecular forces. So this one is for ideal gas. But when it becomes a real gas, the volume of gas molecule becomes significant and the gas molecules attract each other. That means there are intermolecular forces present between them. So we come up with a new equation. We name it as van der Waals equation. Okay, which we insert. Okay, we insert this constant A and B. Okay, so this one is actually, this is for pressure and this one is for volume. Okay, so this equation you just need to know what is van der Waals equation, and you don't have to know in details about the constant A and the constant B. So A and B is a constant which each gas molecule will have its own value for A and B. Okay, what is A? Just to let you know, A is a constant which is the correction for intermolecular forces that present between the gas molecules, while B is another constant which is the correction for volume of the gas molecule. So this is van der Waals equation. You just need to know what that stands for. Okay, so let's have a summary. Okay, so ideal gas. Okay, in ideal gas we made these assumptions. Okay, the first assumption, volume of gas molecule is negligible, and second assumption, no intermolecular forces present between the gas molecule. Okay, so in order for these two assumptions to be met, okay, the gas molecules need to be far apart from each other, and it only can happen at high temperature and low pressure. Okay, secondly, as a real gas, okay, two things that we discover: volume of gas molecule becomes significant because they are close enough to each other, so little space between them. Okay, intermolecular forces present between the gas molecules, since they are close enough to each other, they can attract each other. So attractive forces are intermolecular forces. Okay, so gas molecules are close to each other, and this only happen at low temperature and high pressure. Okay, thank you for watching. I hope you have a clear understanding at what condition does a gas behave ideally, and at what condition as a gas behave as a real gas. So again, the question here is ideal gas is just a theory or is it reality? So do you have your answer right now? So ideal gas is more likely like a hypothetical theory. Okay, so most gas behave as a real gas at most. Thank you for watching. See you guys in the next video. Bye bye.
Let's go.